as Charles mentioned, for our next talk, I'd like to introduce Dave Sharpe, also from the GSC, to present our next talk. So you can go ahead, Dave, whenever you're ready.
I think the screen's on, is that correct?
Yeah, it looks good, Dave.
Okay, so I'm going to talk about the Thorncliffe Formation today. It's a poorly studied sequence observed at the Scarborough Bluffs, and it's situated beneath the regional Newmarket Till. Now, a recent collection of a wealth of high-quality subsurface data allows us to expand those observations north from Lake Ontario to Georgian Bay and develop a conceptual model consisting of subaqueous fan channel system. And this model will be used as a prospecting model for aquifer delineation. Now, below the Niagara Escarpment, there's a Laurentian trough that filled with several hundred meters of sediment. In the map below, we see this surface is covered by thick sediment, so the observations on Thorncliffe are mainly along the lake bluffs of Lake Ontario. So at the Scarborough Bluff sections, below the Newmarket Till, we see about 50 meters of Thorncliffe sediments, interbedded muds, mud dimectons, and sands. The sands at about 130 meters above sea level are inferred to be deltaic or lake level controlled deposits. This sequence is well exposed at the Scarborough Bluff shown here in this image. And to the right, the top 15 or 18 meters show Newmarket Till with a passive contact to bedded sediments below sands and interbedded dimectons. I should note that the Newmarket Till occurs at the top of the sequence. Many people infer that Halton Till occurs at the top. This leads to misidentification or reconstructions in the area. Now, below the Newmarket Till, there's a thick sequence of sediments that Charles referred to as lower sediment between Newmarket Till and bedrock. That's a lot easier to model than trying to sort out these interbedded muds and sands. So we'll focus on that for the moment. So here's a map of lower sediment thickness. All the sediment below the Drummondized Newmarket Till shown here on the right. Thicknesses as up to 150 meters are modeled across this domain. Now, because the stratigraphic units at Scarborough Bluff shown in white here, including older glacial deposits, the Don Interglacial, Scarborough Formation, Potter, they're generally not widely known in terms of their thickness or extent. So we believe the top 100 meters of this sequence is likely Thorncliffe or Thorncliffe equivalent sediments. Now, this thickness of sediments is likely bound on the northwest by grounded ice that actually stopped the drainage of the Great Lakes throughout this period and damming this sediment mass against the Niagara Escarpment, which is roughly 400 meters above sea level. If we look at the regional picture, the Thorncliffe sediments are hard to decipher in terms of their individual formations that have been named, but an upper channelized system, which actually runs all the way to bedrock, is the most readily observable part of the system. And so we see channels in the lower sediments that we think are Thorncliffe below the Newmarket Till. These channels are analogous to younger channels that cut through the Newmarket Till through the complete lower sediment section in places to bedrock. These channels are shown dissecting Newmarket Till in this block model and mapped across the landscape as dissecting the Newmarket Till area. And below that, we show an enhanced view of the Oak Ridges channel system with various depths and thicknesses shown. So the key question is, while we see these Thorncliffe channels arising, how can we map a distribution of them and what is their extent and composition? So what is the observed record? If we quickly look along the lake bluffs, from a section at the Don Valley Brickyards below the regional Newmarket Till. We have upwards from bedrock, the Don Formation interglacial beds, the Sharpe Formation, Thorncliffe muds, Thorncliffe channel sediments, more muds, and Newmarket Till. Now, an enhanced view of the Thorncliffe channel section shown here. These sediments were previously interpreted to be the Pottery Road Formation and inferred to be a low stand, in fact, no ice in the St. Lawrence River Valley. These glacial fluvial characteristic sediments are not likely low-level, lake-level controlled sediments. Next, if moving northward from the Lake Bluff observations, we use these data sets to actually look in more detail as to trying to define the Thorncliffe Formation between Lake Ontario and Georgian Bay. We will highlight on seismic profiles and continuous cores. These data were used, as Charles showed us, to model the area and give us a 3D picture with data support from coded high-quality records and water well records. A perspective view shown here in the lower actually extends from the Niagara Escarpment eastward to the Pontypool wedge of the Oak Ridges moraine. It sort of shows the nature of the problem. The lower sediments are shown here in dark brown, overlain by Newmarket Till and younger sediments. The question is how to parse out the Thorncliffe Formation from this sequence as we go north. We're going to focus on seismic profiles and continuous cores at the following locations: Schomburg, Queens View, Aurora. We not really talk about Markham, and then some pit exposures at the Nelson Pit west of Barrie. To start with, I'm going to show you this overview section shown here across the Laurentian Trough. What we see here are below the Newmarket Till Thorncliffe channels cut through the lower sediment sequence to bedrock in most places. A fill of gravel, sand, clay transitions, very rapid sedimentation. These channels are truncated by the the Oak Ridges moraine channels, truncating Newmarket, the Thorncliffe channels, and lower sediment to bedrock in a number of places. Again, gravel, sand, mud, finding upward sequences. And these sequences are transitional into the Oak Ridges moraine as one continuous formation, two different landforms. These are exceptional events. The sedimentation rates in these features are exceptional. And in fact, they're analogous to Icelandic scale Jökulhlaups, meltwater floods that occur in Iceland today. And if we look at the map on the right, there are flood-scoured bedrock terrains to the north part of Georgian Bay that lead into channels to the south. These channels lead into the Laurentian Trough area, likely feeding these channels that we've seen. The interesting note about the channels on the bottom of Georgian Bay is they go up gradient downflow. In other words, they were cut under pressure. They're likely subglacial channels. So what we see here are thick stratified sequences that are actually deposited by meltwater floods. These are not deposited by ice streams. Ice streams deposit till, floods produce sand and gravel. Now to look at a few details. At the Schomburg site, we see strong high amplitude reflectors on the top of the Newmarket surface shown here, truncated by an Oak Ridges channel. Below the Newmarket Till, we see arcuate reflectors that actually truncate horizontal reflectors here, truncating older lower sediments, showing a Thorncliffe channel with a borehole filled with sands, finding upward and interbedded with rhythmite shown here in core photographs. Similarly, at Queensview, we see two profiles east-west showing channel structures eroding into lower sediments, into bedrock below Newmarket till the core shows 20 meters gravel sand interbedded into rhythmic muds, roughly 400 meters of rhythmite analogous to Schomburg. At Aurora, we see a 2 kilometer wide, 100 meter deep Thorncliffe channel, some shallower channels off to the west. Borehole shows 80 meters of gravel, sand, debris flows into rhythmites. Again, 400 rhythmites shown here in the core photographs. If we summarize the Queensville and Aurora locations, it actually defines the geology of the Yonge Street aquifer. Shown here, what we see here is where you have thick sands and gravels, you have thinner muds, thinner sands and gravels, thicker muds, but the rhythmites correlate the sequence as one continuous depositional sequence. That's the advantage of continuous cores, is we've captured the whole depositional record in these cores. So if we look at the boreholes actually define the geology of the Yonge Street aquifer, if we add the 60 years plus of municipal pumping, we see a strong 20 kilometer long hydraulic connection, north-south, 2 to 3 kilometers wide, becoming kilometers wider in the south where the channel becomes fan-like, as Rick Gerber mentioned the other day. And so we have a channel esker fan system. The paleo flow comes from the hydraulic data connection north-south. A similar channel was identified by Civil in the 70s. I don't have time to talk about that today. And what we have in summary here in terms of the sediment sequence, these fining upwards gravel, sand to mud sequences are well explained by a subaqueous fan depositional model. In this model, you have a high energy jet entering a standing body of water, either proglacial or subglacial. We have gravel facies deposited in the first approximately 500 meters. And then for kilometers downflow, we have various sand facies, ultimately distal going into silt sands and muds. If you go up the sequence, as we do in the sediment column, you move into muds. If you go perpendicular to the gravels close to the source, you go into sand, muds quickly. A little further out. The key thing about this conceptual model is we actually don't know the depth of the water here. All we know is the upper limit on mud deposition. And so this constitutes a conceptual prospecting model for what we're going to show next. Using Charles's modeling skills, we've modeled the Thorncliffe sediments at a preliminary level here using this type of data support that Charles mentioned. It provides areas, prospecting areas with over 100 meters of Thorncliffe sediments shown as anomalies on this map. What we just looked at were anomalies were actually channelized. We're going to just focus on this area for a few minutes where we have these depositional mounds. And we're going to talk briefly about areas of high sedimentation and then the upper limits of mud deposition in the basin. So briefly going to the Nelson pit here west of Barrie, what we see here are very high energy, rapidly deposited sediments shown by these climbing dune structures. So you have rapidly abrading mounding of these sediments. These sediments are analogous to what we saw when we visited the Icelandic outburst flood sequences from 1996, very high sedimentation rates related to these Icelandic eucalypts. In the pit, there's 35 meters of sand and gravel exposed. There's another 25 in borehole. So a very thick sequence creating these mounding structures below the Newmarket till uplands shown in this pit and in several pits to the north. So I'm just going to compare. We look at the channel structures in the Aurora area and we get mounding structures up in this area. So here we have the Nelson Pit. If we go on a transect just east of Barrie, shown here on the right, boreholes from OGS 2013-05, Thorncliffe core sediments under Newmarket till we have 50 meters of mounding. If we look at a transect southwest from Aurelia, shown here, again with the Newmarket capping, we have a 50 to 100 meter mounding of Thorncliffe sediments here. The paleo flow in the Nelson Pit was essentially north-south. And so if we trace the northward flow direction, we see this mounding to the north. One last point, just to the north near Coldwater, we see a fining upward sequence with muds just under Newmarket till up to 325 meters above sea level. That compares with the inferred inference of the Thorncliffe Delta at 130. So we're now 200 meters above that. This is a large glacial lacustrine mud basin. We don't know the upper limit on sedimentation. It's not likely a delta system. So just to summarize, Thorncliffe Formation is a large, thick glacial basin sequence. It's basically 400 cubic kilometers of volume of glacial lacustrine basin sediment, mostly muds with channel fans, feeders, and mounds. The channel fan sediments show characteristic fining upward sequences that explain the subaqueous fan model. There's two prolific aquifer systems that help inform the geological model with hydrological information. These combined data actually give a much better representation of the geometry of these bodies. The deltaic fluctuating lake level or base level controlled model is not supported by these high quality data. And the channel fan prospecting model predicts the sediment architecture of Thorncliffe aquifers in terms of architecture, facies character, trends, orientation, and geometry. This is a brief overview. More is published in this paper that's coming up in the next few weeks. If anybody wants access to this or papers referred to in earlier slides, please contact us. Thanks very much for your time.
Awesome, and thank you, Dave, for